Hey everyone, it's Vin from LearnML. Today we're going to be having a quick look at the motivation behind Monte Carlo Dropout. Okay, Monte Carlo Dropout actually enables you to do uncertainty estimation in neural networks, which at the moment is completely unavailable in neural networks. So this comes from, I think, a 2016 paper. I'll link it in the description. But yeah, it actually doesn't require you to make any changes to a typical sequential feed-forward neural network that's using Dropout as a regularization technique. So if you're using Dropout in any application, consider using Monte Carlo Dropout, because it enables you to do this uncertainty estimation, as well as actually improving your results a little bit. Okay, so I expect you to be familiar with TensorFlow's Keras and also Dropout. And just neural networks in general. And like I said, this is just like a motivation video behind Monte Carlo Dropout. We're going to make more content on this technique in the future, particularly because it's very underdeployed and overlooked. Okay, so to demonstrate this, I'm just going to take the California housing dataset and try to map one variable because it's easier to plot. We're going to try to map median income to median house value. Just in a very naive sort of way, just by fitting a neural network on it. Okay, so of course we split into a training set and a testing set, and also normalize the data using scikit-learn's pre-processing standard scaler to make the data easier to learn. Okay, so this is the architecture that we're using. We're using the self-normalizing neural network, which is the SELU scaled exponential linear unit using, this is the activation function, and then for the kernel initializer, or the weight initialization logic, we're using the LeCun normal, which, like I said, this enables self-normalization in the neural network, solving the vanishing or exploding gradient problem. Okay, and yeah, one input, one output, regression task. This is the summary of the model. We're using mean squared error and NADM as the optimizer. I'm skimming over a lot of this because this is simply to demonstrate what Monte Carlo Dropout does. And then we'll go into much more depth in the future. So, of course, this is what you're used to. A standard neural network's just going to plot some sort of smooth, sort of decent looking output. And yeah, this is very reasonable given the data. Small kink in the middle, but apart from that, looks good. Okay, Monte Carlo Dropout. Now what we're going to do is we're going to inherit from the Dropout module of Keras's TensorFlow's Keras, sorry, and we're going to override the call method. And all that we're going to do is essentially force training to stay on. If you think about Dropout, what you do is you train the model using Dropout. Each neuron has a Bernoulli distribution applied to it, and randomly, as you pass in a training instance, some of these neurons are going to drop out. Okay, cool. When you go to test the neural network, you actually force the neural network to turn Dropout off. So you basically just get rid of Dropout. This is so that each time you pass in an input, you'll get the same output. Okay. However, with Monte Carlo Dropout, we're just going to make the small adjustment such that you keep Dropout on, even in testing. That means each time you pass in an input, you'll actually get a different output because the model changes slightly as some of the neurons drop out. Okay, so we've called this Monte Carlo Dropout in this class here. And now we're going to use exactly the same architecture, but apply Monte Carlo Dropout to each layer. Everything else remains the same, including the optimizer, etc. Okay, we fit the data again. So now we see something interesting. The model is actually finding two different interpretations of the data. So it's finding this interpretation here, and it's also finding this more flat interpretation. When you're doing Monte Carlo Dropout, it's actually been proven that this is approximate Bayesian inference of a deep Gaussian process, And so what you're doing, sorry, I should have explained earlier. What we're doing is we're passing the same input in 10 different times, and we're stacking this in a matrix called ypred stack. So like I said, you get a different output each time you pass in the same input. So we pass in the same input 10 times, and then we plot the output here. And this is where we get this strange looking graph. So each time you pass in the input and you get an output, essentially what you're doing is you're sampling from the posterior of a Bayesian distribution, approximately. And this enables you to do this uncertainty estimation. Why? Okay, well, if you look over here where there's fewer data points given in purple, you see the dispersion and the variance of the red data points, which is the prediction. You see that increase. This demonstrates that the model is less certain here. Whereas where there's the most data points, this is where the model's the most certain. Now, what we can do is we can take an average of these red points, and this output is actually going to be, on average, more accurate than a standard neural network. So to make that clear, if we sample from the posterior 10 times and take an average of the outputs, normally this is actually going to be higher accuracy than just a standard neural network. Now we can display this a little bit more in this weird, crazy looking graph. So again, looking at the red points, but also looking at this gold histogram. The histogram represents how many data points in each bin. So here there's the most data points, and that's where there's the least dispersion of the outputs, the red outputs. Whereas where there's very few data points over here, this is where we've got the greatest dispersion, meaning that the model is least certain. And this green is taking the average, and the average, you can see, gets a very similar shape to the neural network we had at the start, the original neural network. Okay, that's all. We're going to go much more in depth with this in the future to show how powerful this really can be. But for now, I'll leave it at that. Thanks for watching. Bye.